Hi guys, today we are starting in a little bit dark theme because basically the whole last week we had some rain in clouds and stuff like that, but today we have very bright sunshine that basically ruins my light setup. So yeah, believe me, that looks much better than what you would have seen if I did not put this filter on. Right. So today I wanted to show you a problem from a recent Div2 round 737, which like I actually participated in this contest, as we can probably see if we try and wait a little bit. Other force is very slow for some reason recently for me. So yeah, in the contest, to be fair, I only solved AC because I went for E and then E was a little bit, had a little bit too much detail to it, so I couldn't solve it during the contest, but I upsolved it relatively quickly. It's like around 8:30 the upsolving opened, and it took me about 20 more minutes to get accepted. But the problem I wanted to talk about today is problem D, which is Ezzat and Grid. The reason why I wanted to discuss this problem in the first place, because it's it's 22 hard rated, so it approximately fits within the difficulty range that we have for Wednesday. But also, like, I think that's a very educational problem in a way. Very pedagogically good problem. So in this problem, Moment was drawing a grid of n rows and 10 to the 9 columns containing all the digits 0 and 1. As it noticed what Moment was drawing and became interested in the minimum number of rows one needs to remove to make the grid beautiful. Now normally that word should be in italics, but whatever. So a grid is beautiful if and only if for every 2 consecutive rows, so we take the 1 second, take like that row, and they should have at least 1 column containing 1. So like these 2 guys together are good, these 2 together are also good. Ezzat will give you the number of rows n and m segments of the grid that contain digits 1. So like naturally, because of how huge the grid is, you can't just give the entire grid. So what instead happens is that Ezzat gives us segments. So segments work as follows. So first he gives us 3 integers I, L, R. So I is the row index, and left is left position, right is right position. So naturally these 3 numbers indicate a segment within our grid. And he says like, okay, the entirety of that segment has 1s in it. Now live with it. So our task is to tell Ezzat the minimum number of rows that should be removed to make the grid beautiful, right? So then input description happens, segments may overlap, that is, don't care about that too much. We should print an integer k, the minimum number of rows that should be removed, and then indices of rows that should be removed. Now, then we have several examples, but I guess you can pause the video and read through them if you want to, but I won't go through them in too much detail. Alright, so assuming that you did it if you wanted, let's talk about how we can actually approach this problem. So one natural approach would be like as follows. So if the number of columns was smaller, let's say 1000, then we could do something as follows. Let us build a DP array. So DP array of lengths, let's say from 0 to whatever maximum value is. So let's call that capital M. That of course is not possible if we have 10 to the 9 columns, but we'll deal with it later. After all, you can probably guess that coordinate compression will help here, or may help. So I will write it straight away. Coordinate compression. Coordinate compression. Yeah. Let's do this. And we'll talk about it more when we get to the implementation part of the problem. Because that's basically like a technique to reduce some of huge values when the majority of them are empty or similar in a way. So we have this array dp. Now we want to process rows one by one, and what we do is like, okay, we want to make the largest possible grid in terms, largest possible beautiful grid in terms of how many rows it contains. So naturally we can say like, okay, let's see, what if for each index from 0 to maximum value, we keep the size of the largest beautiful grid up to that point, such that the last row of that grid has 1 here. So let's say here size is 3, here size is 2, something like that. Here size is 1. And potentially somewhere the size is actually 0 because no columns so far had, no rows so far had this column filled. Why we are interested in this thing? Because in DP, you're in such a row DP, you are trying to append a row to your partial solution. Like full solution is the largest possible grid, partial solution is the largest possible grid up to some point. So let's say up to this point. So for this, for example, like you can see that for this guy, the DP at this point looks like, well, 1, because we can't take that body, and a bunch of zeros, and 2 because we can take both of these guys, and 1 again, bunch of zeros, and then here you may say that it's 1, but in fact that's 2, because these two together form beautiful grids, and the last row of this beautiful grid has a 1 here. Now, why do we actually want this value to be 2? Because then we will append this row, and we can append it to whatever grid it has 1s in common with. Like we can append it here, which in turn is appended here. So after we process that row, we would naturally expect here to be 3, which is 2 plus 1, not 1 plus 1. So yeah, hopefully the DP definition was clear enough. So like DP at ij is the size of the maximum beautiful grid consisting of rows from 1 to I, such that the last row has 1 in j's column. I encourage you to take some time to process that information because it may be a little bit confusing. If you were not thinking about this problem for long enough as I was, it may not be the most natural choice, but believe me, it will lead us to a good solution. Alright, so assuming that you fully understand the definition of DP, it should be clear that what we actually want to do, like what is the DP transition from DP of I to DP of I plus 1. What happens is we want to add this row and say like, okay, it has several segments in it. We can append these segments to whatever has something here, here, or rather I should say to whatever has something here. Differences, however, if we append this here, the size of the beautiful grid will be only 2, whereas when we append this one here, the size will be 3, because this in turn is appended here. So naturally we choose the maximum of such values. So what happens is we take maximum over all segments of the I plus first row in dp of I, and we say that all these values that have 1 in them get the maximum of the p of I plus 1. A little bit more formally, so let's say a capital J of I plus 1 is a set of a capital J of I plus 1 is a set of columns that have 1 in I plus first row, and dp of I plus 1 J has 2 options. So first, if J is not in capital J, then the value is 0, because you cannot have last column to be 1. Or rather, because we don't care about like this specific row, we said we care about the largest possible grid, beautiful, that has 1 in this column. So for example here, this should be actually 2, so we just take the previous value, not 0. Be careful about that. So we take dp of I, j here, no change. Now assuming that j is in the set capital J, we should take m plus 1, where m is nowhere related to that m, where m is maximum over j in capital J of dp ij. Now that's how like this thing actually explains why these two are connected, why this is appended here. Because we first take maximum over all previous segments, so like this. First take maximum over all current segments. So like we say, okay, we can apply, we can append any value here to any value here above them. So like, okay, so we can append both of them here. That's why this actually works. Now, unfortunately, if we do this, our complexity will be of m prime times n, when n is the number of rows and prime is the number of columns. Not exactly what you want. So, coordinate compression can help us reduce that to, actually that is small. Coordinate compression can help you reduce a capital M to small m, which is the number of segments. Because naturally, like, you don't care about all points that are not the endpoints of our segments. That is a thing that we will see in more detail in the implementation section once again. But then again, like, this is too slow. This is quadratic in an m. That's not ideal to fit into 2.5 seconds. So now comes the very pedagogical part of it, and namely, like, we have some dp, right, that works in quadratic time. We want to optimize it. What is the natural technique of optimizing dp? Well, sometimes you can notice some minimax properties that like help you process squares and all one time, but more common approach is of course to use some data structure to help us with our dp state. Now for this we need to analyze operations that we have in our dp. So one operation is finding maximum. We underlined one operation is finding maximum over basically subsegments. Another operation is assignment over basically subsegments. So the natural idea that comes to mind is, okay, which data structure can process segments assignments and range maximum queries? Well, that is, of course, a segment tree. So let's just write a segment tree that can do all of that, and that will be it. That will be it. So I want to underline this, how important it is to optimize a quadratic DP with a data structure. That takes a little bit more space than I wanted it to take, but yeah. Because that is just very, very important point that I'm trying to make. So yeah, and then well, like, in case you did not know, but probably you did and did better than me. So there exists a segment tree can do many range operations. Range queries operations in off-log time. That is another important concept if you want to solve problems like that. Hold on. I should be able to get that like here. So yeah, that is like the general overview of how you may want to think about such problems. Now, I believe that it will tell you more if we just look at the implementation section, which I do have open here. Let me make it a little bit bigger so that we can actually see something. Also, our ideas are now located in a more centralized manner. So, the way I did it is fairly bad. You can do so much better, but obviously yeah, I did not care too much about making it beautiful. I do have a template because that usually helps. Like, you want some time to represent what happens in your lazy part of the segment tree and some time to represent what happens in your tree part. Now this part is more or less standard, apart from several exceptions. So, because we also need to restore the answer, like which rows we actually take into our maximum beautiful grid, our segment tree will contain pairs of integers denoting not only the DP value, but also the row which is lost for the corresponding value. There are several rows, we can take any one of them that want to affect the answer. Want to affect the size of the answer. So like problem-specific parts come, of course, here, like what you initialize your segment tree with. If your types T and L are custom types and not just pairs, then you can, of course, like define a default constructor for that, and call T here and L here. But I was a little bit too lazy to define a custom type, so I just went with this. Now here we just assign because our operation is range assignment. In general, you may want to have a combine function that takes in this body and assigns the result of combining them to this body. More or less the same here. Here again, you want to assign a default value. The value of -1 indicates that we don't have a value to assign, just in case you were wondering what that's about. Because our values are non-negative, we can always use -1 as a sentinel. Now query works like left greater than right, we return default value once again. Default value of T. If our segment perfectly matches, then we return corresponding entry of a tree. Otherwise, we want to make a push. We want to split our segment in two. We want to, again, this is a low-cost combine function for 2 tree vertices. We want to return maximum, but we can't just take maximum, guys, because we also need a last row. That comes from LP and RP variables. And update is very similar, and that's actually why I write them this way, because then they are just the same. Like if-else structure, very similar. You can see like if left greater than right, we return nothing because update does not return anything. If the segment matches, then we update tree value and we also update lazy value, which is a little bit bad. Like that we have T and L are technically different types, but I assign here boss. That should be a combined function once again of T and L, but like, hey, nobody said anything bad when I did that, so that is of course a very bad version of segment tree. But I was a little bit too lazy to write custom combined functions for something as simple as pairs. Sometimes I do, however. But here you can see that it's more or less the same, so we like just push the current vertex because we always want to make sure whenever we do anything in a vertex, it's pushed, so like there are no pending updates to it. Again, split in half, process children, combine back into the tree, like update the tree function with combine. So you can see that I could have saved some code here and here, but I thought that, well, I'm a little bit so lazy, I will just write a couple more lines. So here just the input reading happens. We have a vector so that we have our segments split row by row. Then coordinate compression happens, because I did not want to write an implicit segment tree, which can live without coordinate compression. So the way I did coordinate compression, I take a set because I will need it to be sorted either way, so I just insert all endpoints. Then I want to compress each endpoint so that it gets a index from 0 to maximum to number of coordinates. So I loop our coordinates, they are sorted because that's a set. That's why it's not an ordered set. And I set a compression, like this coordinate will get mapped to the current size of the compression. So like first gets mapped to 0, next one gets mapped to 1 naturally, etc. etc. You could call compression reserve some size, or rather for an ordered map I believe that you can supply a constructor argument that will act as a hint for the expected size of the map. Then I compress all the coordinates by looping with like reference. I have parents because like each row actually has only one parent. I have my segment tree of pairs. I make very simple queries and updates for every segment in current row I query. for maximum and parent of that segment. If maximum is greater than update boss, then I say like, okay, overall segments after I completed all queries, I can make all updates with maximum +1 and current row as the last one. Then I need to restore the answer. I do it by querying the entire tree. Like, okay, I definitely take that segment. Then I look back using this helpful parent array. The reason why I need it to be separate because DP overrides parents all the time, so I need to make sure that I store my parents somewhere safe. So then I just use this to have like to find all the rows that I do take. For some reason, the author wanted us to find the values which we skip, which introduced a little bit more code, which was not really necessary, but whatever. So originally I said like, well, we skip everyone but the guys that we take, and technically I have a -1 here, so I have an extra if here. And I just say like, okay, maximum is how many we take, so that's how many we skip. Then I just loop over guys in sorted order and find whoever I skip. So that's it. That's it. Yeah, but I really wanted to share this problem with you guys because I find this general reasoning quite common, that you get a quadratic DP and you want to optimize it to be n log n with some data structures, and often segment tree helps here because your operations are some range operations which naturally map to segment tree. Now I want to say that there is a simpler solution to this problem. Simpler in terms of the implementation, but actually a little bit more involved in terms of reasoning. Now you may have noticed that our parent array stores in some way it stores a rooted tree with root of -1. Now you can map all intersections between rows into not a tree but a directed acyclic graph, and then you can just compute the length of the longest path in that graph. So implementation side, it will be very simple. What is not simple is that longest path is computed in of v plus e time. So we need to take care that we don't have quadratic number of edges. And there is a smart trick which I've also found a recurrency. It's like when you have a graph with quadratic number of edges, you may want to reduce that number of edges, but there is no general rule to how you do that, as opposed to our segment tree solution. But we may take a look at some more problems that require like graph compression sync, which also helps you to take it from quadratic number of edges to something smaller so that you can write your normal graph algorithms on them. But for now, that's all I wanted to show you. Once again, sorry about that a little bit dark theme. But I hope you enjoyed and learned something new today, as always. If so, well, you know what to do. You can tell your friends about this channel. Maybe they will also find it useful. Or maybe you want to keep it to yourself to get an unfair advantage in future contests. So that's up to you. But from me, well, I said that I'm open to problem suggestions. But the only problem suggestion that we got yesterday was to solve hard LeetCode DP problems. Well, I hope that in a way we have hard DP problem here. So I hope that this sort of answers your request. But overall, I was meaning like code forces and add color problems because lead code, to be honest, is not all that interesting. So yeah. Once again, guess you're wondering how we got here, why it's so dark, is because the very bright sunshine ruins the entirety of light setup, and I couldn't fix it fast enough, so I just decided to switch to that team. Maybe we maybe that will be a recurrent theme in case we get a good feedback on it. So definitely leave a comment if you want to suggest a problem, if you want to like I don't know, if you have other suggestions, stuff like that. Once again, I hope you learned something new, and I'll see you soon in another episodes, I guess, of this series. I I kind of don't want to call it a series because that is just like some daily practice that I do, and I'm happy to share it with you because some people do find it educational. So yeah, see you tomorrow, guys. Bye.